Thanks everybody from the field that's joining us today. We're going to have a really interesting deep dive into some CSAT-derived work with channel deepening, looking at shoaling. Excited to see that. I'll let Rachel introduce the whole team that worked on this, but it was recently presented at the RD24 and it was well received, and we have a lot of really cool insights that this team's been working on over the last couple of years. So it's a worthy endeavor to participate in this call today. And for those of you that need credit for your professional development hours, PDHs, I can help set those up for you. If you need that, just send me an email. And we just, hope that you can throw in any feedback or any questions up in the chat box. We'll try and keep an eye on that or get back to it a little bit later in the discussion today. But with that, I will let Dr. Rachel Bain take it away.
Yeah, thanks, Tanya. So I noticed in the invitation that Tanya sent out for this presentation, she described it as our adventures in looking at deepening and shoaling, and I thought that's sort of a profound way to put it because they're definitely adventures. Lots of trial and error there. Not as many successes as we would like, but definitely an adventure. So the topic for today is, of course, this question of whether shoaling accelerates after a navigation channel is deepened, and then how we can use tools developed by ERDIC to help address that question. And as Tanya said, this is a presentation that Michael and Anna and Katie and I gave for RD24 a few weeks ago. So if you were at RD24 and you already saw this presentation, none of us are going to feel bad if you leave or log off right now because this is recycled content. But for those of you who weren't able to attend our presentation back in April, we wanted to do this again as a CIRP TD to try to connect with a broader audience and hopefully draw on our community's collective experience or collective expertise about this topic. So in terms of getting your expertise, I'm just going to tell you up front what the open questions are and where we could really use some feedback. I know some people start out their presentation with a question, and then at the end of the presentation, they tell you what the answer is. I'll just warn you right now, this is not one of those presentations. This research is still very much in the active stage, and we don't have the answers to a lot of these questions yet. But the things that I hope you will be thinking about during this presentation are so these 4 bullet points. First of all, for those of you at districts or working closely with districts, what sites are you working on or have you worked on in the past where the shoaling rates have gone up after deepening? And then related is the second bullet point. Have you ever worked on a site where the shoaling rate has not gone up after deepening? And that's what we're really going to be focusing on today. And then following up on those first 2 bullet points, we have our third bullet point. Have you personally seen any patterns or identified any patterns, or you just sort of have this little idea in the back of your head that there might be a pattern concerning where the shoaling rate increases after deepening versus where it doesn't? I just threw some ideas up there, which just maybe they're right, maybe they're not, I don't know. Processes like a tide-dominated versus a river-dominated system, or the level of wave energy, the location within the system, or even the location within the reach. Any patterns that you personally might have seen. And then finally, we are looking for records of dredging volume that we can use to validate a lot of the ideas that we're working on. So I hope you will be thinking about any data that you might have sitting on a 3.5-inch floppy disk in a filing cabinet somewhere that you might be willing to share with us as we move forward with this project. Okay, so I don't want to spend too much time today getting into the theory, since I think we already have a pretty well-informed audience. But just in case there's anyone on this call who isn't already familiar with this topic, let's spend just a few minutes getting everyone on the same page about why we would expect a navigation channel to shoal at a higher rate after deepening. So there's a few relevant physical mechanisms that we need to consider in this context. And the first of those is that if you dig a wider, deeper hole in the bed of your water body, it's simply going to be more effective at trapping sediment. So in the example on the screen, we have the pre-deepen channel on the left, and then we have a cross-section through the post-deepen channel on the right. And what we're seeing in this diagram is that the shallower channel is less likely to trap sediment because the suspended sediment can easily hop over the channel, and the bed load, which falls into the channel, gets remobilized by waves and hops right back out. Once that channel is deepened in the right frame of this image, that suspended load can't hop over the channel anymore, so it falls in. And once the sediment gets into the channel, it has a really hard time getting out because it's below wave base. So that's one reason why the shoaling rate might go up in a deeper channel. Another reason that deeper channels might shoal at a higher rate is because the deepening facilitates salt wedge formation, and that leads to flocculation and the settling of fine sediment. So the example you're seeing on the screen right now is from a dissertation that came out of the University of New Orleans, and they're looking at the salt wedge in the Mississippi River. So this top plot up here shows the salinity in June 2012 from New Orleans on the left down to Head of Passes on the right. And the lower plot then shows the settling velocity of clay in the water column. So the darker blues show where the clay is settling out the fastest. And you can see there's a really clear correlation between the salinity and the settling velocity. And that's because of the chemical interactions between the salt water and the clay particles causes them to stick together, the particles get bigger and they sink faster. So that can cause higher shoaling rates in deepened channels. Another reason that deepened channels might shoal faster is because tidal deformation can enhance sediment import into the channel. So the flow chart on the screen is from a paper looking at the Ems estuary in the Netherlands. And what they were looking at here is how deepening the channel, so we start here on the deepening portion of our flow chart. So deepening the channel results in a reduction in the frictional dissipation of the tide that causes the tide to amplify. The amplified tide has higher flood velocities and that imports more sediment into the channel, which in turn further reduces the hydraulic drag in the channel. And we get this runaway train cycle where the estuary enters a hyperturbid state where it's importing massive amounts of sediment. And then finally, the last reason I want to look at is that larger channels can accommodate larger vessels, and larger vessels tend to produce larger wakes. So if larger wakes then cause bank or bed erosion, that sediment has to go somewhere, and the argument might be that it ends up in the channel. Now, for the sake of argument, I know someone's going to mention it, so I just want to point out that there are also a few physical mechanisms that might prevent the shoaling rate from increasing after deepening. So one of those is the traditional tidal prism inlet area relationship. So like I said on an earlier slide, if we deepen the channel, we reduce frictional dissipation of the tide, and that allows for a more efficient conveyance of water through the channel. And that then in turn allows the tidal prism to increase. So I'm really simplifying things here and ignoring a lot of potential feedback cycles and other things that can happen, but just keeping things very simple. If we hold all else equal and just increase the tidal prism, we might also increase the velocity, which would favor scouring. So that's one reason why a deepened channel might actually see a decreased shoaling rate. And then the second thing we need to think about is that if a system, well, all systems have a finite volume of sediment available, and if our system happens to already be trapping 100% of the sediment in its pre-deepened state, then deepening the channel isn't going to have much of an effect on shoaling rate because there's no extra sediment available for the channel to trap. But in spite of those counter-arguments or situations where we could argue that no, deepening the channel isn't going to increase the shoaling rate, I know that I have personally had it pounded into my head for years that the shoaling rate should be higher in a deeper channel, like period, full stop, end of story. And this was an idea that was so firmly in my head that when Tanya reached out to me in June of 2023 and asked me to explore whether deepening increases shoaling rates, I legitimately thought she was joking. So those of you who know me well know that I often have trouble figuring out when something is a joke or isn't a joke. So this is a screenshot of the subsequent conversation with Tanya where I was trying to clarify whether she was actually joking when she told me to look at this. And I think my commentary here is pretty reflective of maybe all of our mental framework surrounding this idea. So just going to quote a very naive 2023 version of Rachel. It seems like a no-brainer that a deeper hole will trap more sediment. So, spoiler alert, 2024 Rachel is now going to spend the rest of the presentation showing you that 2023 Rachel kind of stuck her foot in her mouth and definitely had a lot to learn about deepening and shoaling. Okay, so let's get into some actual data now. So where did this idea come from? Like what data do we have to back this up? Well, here's one example. So this is a plot of the cumulative volume of sediment removed from the entrance channel at Freeport, Texas over 3 decades. And these data were compiled by Dr. Julie Rosati back in 2005. And I think this work has basically become like this seminal example of how shoaling accelerates when a channel is deepened. So for anyone who's unfamiliar with like what we're looking at here, on this concept of cumulative volume, basically each point on the graph is the volume that was dredged during the plotted year, plus all of the volume that was dredged leading up to that year. So we get this monotonically increasing series of points showing the total volume of sediment that has been removed from the channel up to that point in time. So then when we fit a trend line to these cumulative volumes, what we end up with is a representative or a typical shoaling rate over the duration of interest. So what you're seeing here is that between 1971 and 1992, the channel was shoaling at about 750,000 cubic meters per year. But then the channel was deepened in the early 90s, and from 1994 to 2004, the shoaling rate increased to over 1 million cubic meters per year. So just by glancing at a plot like this, we can immediately see that if the slope of that trend line increased after deepening the channel, then we know that the shoaling rate went up in association with that deepening. And here's another of Julie Rosati's examples from the St. Mary's Kings Bay channel at the border between Florida and Georgia. And again, we're seeing the same pattern. The slope of the trend line is lower before deepening and then higher after deepening. And that indicates that the shoaling rate went up significantly in association with that deepening. We can also look at this idea by considering shoaling on a reach by reach basis. So in this figure, you are looking at a longitudinal transect along the Houston Navigation Channel. We have downtown Houston over here on the left side of the plot, and then the Gulf of Mexico is on the right side of the plot. The blue points on this figure show shoaling rates on a reach by reach basis before the channel was deepened, and then the red points show the shoaling rates after deepening. And in general, what we're seeing is that those red points plot higher than the blue points. There are a few local areas like here and over here at the very head of the channel where the shoaling rate is actually a little bit lower after deepening, but overwhelmingly we're seeing that the shoaling rate did go up in almost all reaches after deepening. And then this is the part where I tell you that I stuck my foot in my mouth. We found this data. So these are data from the main ship channel in San Francisco. If you're not familiar with San Francisco, the main ship channel is the entrance channel crossing the Ebb Shoal. And these numbers looked weird. So on the left side of the plot, we see successively increasing depth in blue, orange, and yellow. And you can see that the shoaling rate actually went down a little bit between the blue points, which is partly 45, partly 50-foot depth channel, and the orange points, which are the 50-foot channel. So that's kind of weird, but those numbers are pretty close. So, you know, maybe that's just measurement uncertainty. But overall, there's not much change here between 1950 and 1980. And then we have this gap in our data set. We weren't able to find any data for 25 years. And then we found more data from 2020 to 2020, and we saw the shoaling rate has been cut in half, even though the channel dimensions hadn't changed. So I saw this and I got really excited. I was like, oh, the boundary conditions must have changed. Maybe this is due to sea level rise. Maybe this is due to land use change in the basin. Like it looked like a really exciting mystery for us to figure out and solve this problem. Then we contacted San Francisco District, and they told us the reason the dredging volume had been reduced in the channel is because they have stopped maintaining the channel to the full authorized depth. So technically this fits within our paradigm. The shoaling rate has gone down because the channel dimensions are now smaller due to lack of maintenance. And then we saw this data. So these are from the Calcasieu Ship Channel in Louisiana, and I saw this right after I had seen the San Francisco data, and I was like, yep, I know what's going on there. I saw the same thing in San Francisco. They must not be maintaining the channel to full depth anymore because obviously the shoaling rate went down. And if the shoaling rate went down, that's what that means. Like I said earlier, 2023 Rachel was very naive and really enjoyed sticking her foot in her mouth. Jack Cadigan and Liz Holzenthal have both been working on this problem, and it turns out that Rachel was wrong. 2023 Rachel was wrong. The most likely explanation here is that it is some change in boundary conditions that have led to this reduction in shoaling rate. So this is an example that definitely doesn't fit within our mental model. The shoaling rate went down even though the channel dimensions stayed the same. And then we stumbled across this plot, and this is again looking at shoaling rates in the Houston Ship Channel over a longer span of time than we saw previously. And look at this. So deepening the channel up to a depth of 34 feet, which is the white squares down here, that resulted in a consistent increase in the shoaling rate. But then they deepened again to 36 feet, and the shoaling rate dropped by more than half. And then they deepened to 40 feet, and the shoaling rate dropped again. And the shoaling rate only increased recently during the most recent deepening to 45 feet. So these inconsistencies in behavior just really didn't line up with our team's deep-rooted understanding of how these systems are supposed to behave. So we kept digging and digging and digging. And we stumbled across this paper from the 1960s. So this is about the Savannah Navigation Channel. This plot's a little bit different than the other ones we've seen. So you're looking at time on the horizontal axis, but then the vertical axis shows an average shoaling rate for a given set of channel dimensions. And what we're seeing is that for the entire project, which is represented by the green squares, the shoaling rate did increase as the channel dimensions increased. But for this orange reach here near the mouth of the channel, which is shown by the circles on this plot, what we're seeing is a consistent decrease in the shoaling rates as the channel dimensions were increasing. So it appears that the odd behavior that we saw at Calcasieu and at Houston might not be all that anomalous. It appears to happen more often than we like to acknowledge. And we have reports dating back to the 1960s, which are documenting this. Simply speaking, deepening a channel does not always result in increased shoaling, and conversely, a decrease in shoaling doesn't always mean that the channel dimensions were reduced. So, summarizing what we've seen so far, our coastal research community has this sort of deep-rooted belief that if you deepen a channel, the shoaling rate will increase. And there are quite a few physical mechanisms that would cause that to occur. But despite there being a number of commonly cited examples where deepening the channel did increase the shoaling rate as we expect, there are also a number of data sets that show that this isn't always the case. Sometimes the shoaling rate actually decreases when the channel is deepened. So for the rest of the presentation, we're going to take a look at how USACE tools and data sets that we're in the process of developing can be used to provide more insight into the shoaling deepening relationship. Okay, so one of the main tools that we have developed to evaluate shoaling in our navigation channels is the core shoaling analysis tool. If you have any questions about how CSAT works, Michael Hartman is our amazing CSAT guru, and you should ask him because he knows everything. So CSAT is a publicly available open source suite of Python routines which are used to analyze district hydrographic surveys. We use it to quantify historical shoaling rates and then predict future maintenance needs for the channel. And all of the CSAT code is constructed on surveys from the USACE eHydro database, which you're seeing up here on the screen right now. We're almost up to 100,000 surveys. And this is just a centralized repository for all of our hydrographic survey data dating back to at least 2012. So what CSAT does is it downloads that bathymetry from eHydro and it reprocesses the raw XYZ files into a format that facilitates further calculations. So the first step in that process is to grid the data onto a consistent 10-foot by 10-foot grid. So you can see an example of the gridded bathymetry in the image on the left side of the screen. So the position of each pixel on this grid remains constant through time. So what we can do is we can either look at maps of the bathymetry at a single timestamp. So in our space-time cube here, that would be this green slice is just a map of bathymetry at one point in time. But we can also look at a time series of bed elevations at a single position, which is this blue stack of pixels here. So it's a single point looking at bed elevation through time. All right, and then the final step in the CSAT algorithm is to analyze shoaling behavior at each individual pixel. And that was something that really confused me when I first started on this project. So I want to emphasize that this is a pixel by pixel analysis. And I think the best way to explain this is to just walk through an example. So that's what we're looking at in this figure. On the right side of your screen, you're seeing a time series of bed elevations at a single pixel. And each of the blue points on this graph is the bed elevation at a distinct bathymetric survey. So at this pixel, the bed elevation starts out at about 27 feet deep, and then we shoal to about 25 feet deep, and then there's dredging, which decreases the bed elevation. So now we're down to 28-ish feet, and then we keep increasing and dredging, and then up and down and up and down. So what CSAT does is it calculates the shoaling rates for each pair of bathymetric surveys, which is not disrupted by dredging. So each of the black lines in this figure is one valid shoaling rate. And then the final step is the algorithm is that it averages all of those rates together to get a typical or a representative shoaling rate at that pixel, which is used to generate the forecast, which is indicated by the dashed line in the figure. Okay, so that's CSAT. For the rest of the presentation, we're going to transition into a case study of how we can use the CSAT products to provide more insight into how navigation channels shoal. So everything I'm about to show you is based on reimbursable work for Savannah District. I'm very grateful to Anna Godfrey and Katie McFerrin for sharing these results with us. So the Port of Savannah, this is on the border between Georgia and South Carolina. This is one of the largest tonnage ports in the United States, and it's one of the many, many projects that has recently been deepened to accommodate larger vessels, like the ones shown in the pictures on the screen. So the entrance channel, which crosses the Ebb Shoal, was deepened to 47 feet beginning in 2015, and then the inner harbor was also deepened to 47 feet beginning in 2019. So in a traditional shoaling study within that paradigm we talked about earlier, we would probably see that the channel was deepened by 5 feet, and we would ask ourselves, how much has the shoaling rate increased? But given what we've seen so far in this presentation, I'd like to think about some more nuanced ways we might ask that question. So rather than asking how much, we might first of all ask, has the shoaling rate increased? Where has it increased? If it hasn't increased, why not? And what physical processes might be driving the behavior that we're seeing? Okay, so we're going to start out by looking at how shoaling behavior varies in this channel at fairly coarse resolution in both space and time. So what you're looking at on this plot is the average shoaling rate in each reach before the channel was deepened, that's shown in purple, and then after the channel was deepened is shown in the light blue. And this is for a transect which extends along the entire length of the Inner Harbor from the channel terminus here on the left side of the plot to the jetties here on the right side of the plot. We've got distance along the channel on the horizontal axis, and the shoaling rate is on the vertical axis. Now remember, our mental model tells us that if we deepen the channel, we expect it to shoal at a higher rate. But to a large degree, that is not what we're seeing on this plot. There are a couple of reaches at the innermost portion of the harbor where the shoaling rate has gone up after deepening. But in most of the other reaches, what we're actually seeing is that the shoaling rate has gone down, or there are a couple places where the shoaling rate has essentially stayed the same. But overall, broadest interpretation of these results are that the Savannah Inner Harbor is actually shoaling at a lower rate now than it was before deepening. So that was the reach level. The CSAT products also allow us to look at that behavior on a pixel level. So what you're looking at on this slide is the CSAT calculated shoaling rates for each pixel in the channel on that 10-foot grid. The shoaling rates on the left side of the screen are color-coded so that if sediment is accumulating, it's shown in orange hues. Scouring is shown in the purple hues. And then the shoaling patterns for the pre-deepen channel are in that top figure, and the post-deepen channel are in the lower image. And then over here on the right, we're looking at the difference between the two rasters. So if the shoaling rate increased after deepening, we're seeing that in pink. And if the shoaling rate decreased after deepening, that is shown in green. And what we're seeing here is that the overall trend in this reach is for the shoaling rate to decrease after deepening. There are two big exceptions to that pattern, which are, if I can get my cursor working, here and here. And you'll notice that both of those occur at the inside of bends. Our team is still working to figure out why this is happening, why the channel is broadly shoaling at a lower rate now, except at those two locations. But one possible hypothesis that we have is that the deepening destabilized the side slopes at those two pink regions and is causing the sediment to travel downslope into the channel at those two sites. One more example of this pixel level behavior. This is the same color scheme as before. So net accumulation of sediment is in orange, scour is in the purples. And then on the right, if the shoaling rate went up, that's in pink. If the shoaling rate went down, that's in green. And there are a couple really interesting things to look at in this figure. But the main thing I want to focus on is how the shoaling rate is lower in the center of the channel and higher at the channel margins. And again, we're still trying to really work out the physical mechanism behind this. A couple possibilities we've come up with are that, first of all, possibly prop wash from commercial vessels is disturbing the bed in the center of the channel, and that sediment suspended by the vessels is being then deposited in the more quiescent areas at the channel margin. You'll also notice that the area of scouring is enlarged in the deeper channel. So Anna Godfrey is hypothesizing that maybe deepening the channel has increased the tidal prism and therefore the current velocities through this reach. So we're seeing enhanced scour. But whatever is causing this, you can see in the right image that the overall effect for this reach is a reduction in shoaling rate, even though there are some areas, especially at the channel margins, where sediment has started accumulating at a faster rate. And finally, the really complicated plot. So up till now, we've been looking at sort of a time averaged behavior. We are now going to get as close to instantaneous behavior as we can. I have instantaneous in quotes because it isn't truly instantaneous. We're looking at discrete surveys, but this is looking survey to survey, so as close to instantaneous as we can get with this tool. So this is the absolute finest spatial and temporal resolution that we can look at with CSAT. And what we're looking at here is the distribution of pixel level shoaling rates as a function of the pixel's starting depth. So as an example, I know this is a really complicated plot, but if we take a vertical slice through this plot, so let's say at 44 feet starting depth, we take a vertical slice along this line. If you can imagine, so we've got our low percentiles moving into higher percentiles. You can imagine if you sliced through that and looked at it on its side, it would be some sort of bell curve, and that's showing the distribution of shoaling rates for pixels with a starting depth of 44 feet. And then we repeat that for all the possible starting depths and get a distribution of shoaling rates. So there are a couple main things I want you to notice about this plot. And the first thing I want you to notice is that the black line here across the middle of the plot, which is the median shoaling rate, is very nearly flat. It's slightly sloped upwards. There is a slight slope if you zoom in on it, but it is pretty close to flat. So that tells us for a typical pixel in this reach, the shoaling rate is independent of depth and it's pretty close to 0. The second thing I want you to look at is the first percentile, which is the lightest blue color down here that I'm trying to highlight with this cursor. And you'll notice that there actually is a trend here. So the blue, that light blue region is sloping upwards with depth. And that tells us that shallower pixels on the left side of the plot are more likely to have extreme scour events than the deeper pixels. So, broad interpretation of this plot. In terms of like extreme events, like extreme scour situations, there is a pattern of shallower pixels being more likely to scour and deeper pixels being more likely to shoal. But what we're seeing here is that for a typical pixel on a typical day when there's nothing extreme happening, shoaling and depth really don't have that much of a relationship. So one thing we've been asking ourselves as we look at these results is this an accuracy issue? Maybe part of the reason that we're seeing the deeper channel shoal at a lower rate is because CSAT isn't accurate enough to capture the change. So to evaluate that, we've been comparing the CSAT-generated shoaling rates to data from across the United States where we have independently reported dredging data, and this is the outcome of that analysis. So on this plot, we have the reported annual dredging volume on the horizontal axis, and then the shoaling volume calculated by CSAT is on the vertical axis. And we would expect, if CSAT is doing its job, we would expect these values to be identical and plot on the 1-to-1 line. And we're not quite there. If you are a benchtop chemist or a particle physicist, seeing that the CSAT volumes are off by tens of thousands of cubic meters, it might be kind of jarring. But as we look at this plot, just saying, we need to remember that within the field of sedimentology, if you are measuring something to better than order of magnitude, you are doing a pretty good job. So I would say that our team as on a whole is actually pretty happy with these results. This validation is still a work in progress, and we would love to get some more use-based projects into this analysis, but as it turns out, finding shoaling records is actually not a straightforward task. So I'm just going to take advantage of the captive audience right now, go back to those questions from my first slide, and say that if you are from a district, if you're working on a project with the district, you have friends at a district, which is everybody here, if you happen to have records of dredging volumes for a project that isn't already on this map, we really hope you will reach out to our team. We would love to find a way to data share and get as much data involved in this analysis as absolutely possible. Okay, so let's wrap this up. This brings us to the big picture question of channel management and what the implications are for managing our navigation channels. So what are those implications? That is a complicated question. So to hammer home the complexity, Katie McFerrin made us these figures comparing two different reaches in the Savannah Inner Harbor. So the reach on the left, this left plot, is this yellow reach near downtown Savannah. And then the reach in the right plot is this orange reach just outside the jetties on the ebb shoal. And like we were seeing before, the purple line, it shows pre-deepening shoaling rates, and the blue line shows post-deepening shoaling rates. And both of these are a function of depth. So we have depth on our horizontal axis, shoaling rate on our vertical axis. And what I want you to take away from this big picture is that there is not a consistent pattern. What we do see consistently is that deepening the channel alters the shoaling behavior in some way, but the way that the behavior is altered varies from reach to reach. And when Katie sent me these results, she asked me to emphasize that these observations make it extremely difficult to make any sort of sweeping generalizations about the effect of deepening on shoaling. The results we obtain are likely to be system dependent, even reach dependent, and maybe even time dependent. If the channel has not equilibrated yet, you might get different results compared to what you would see in the long term. So in terms of management implications, if you modify a channel, you should expect its behavior to change. But you should not expect its behavior to change in a cut and dried way. All right, so a few concluding points, and then I am going to open it up for questions and discussion. We have this paradigm, or this understanding in our heads that if you deepen a channel, if you enlarge a channel, if you widen the channel, you're going to increase the infilling rate. But what we've seen over this presentation is that even though there are examples where that's true, there are also a lot of examples where that is actually not true. And we have known this since at least the 1960s, although we, or at least I, apparently have forgotten that. And we see this through our CSAT analyses. We see this occurring at spatial scales that range from tens of feet, so individual pixels, up to the entire project, and at temporal scales ranging from days in the CSAT analysis up through decades, as we see in the historical records. So like I said, 2023 Rachel was kind of naive and liked to stick her foot in her mouth, but I'm just going to put a positive spin on this and say that this is a really exciting opportunity to remind ourselves of things we may have forgotten, and revisit some of those knowledge gaps so we can work out how these systems work in a more comprehensive way. Yeah, so with that, I would like to open it up for comments, questions, observations. If you have any questions at all, please contact one of the people on the slide. We would love to hear from you. Yeah.